Thank you. My name is Liang Yan. I'm software engineer from the SUSE Labs. As you may notice, I'm the third presentation from SUSE today. So I think before we start, really thanks the OLF to provide this opportunity for me, for SUSE. And thanks for all your time here, to spend the time here. Hope you could find something enjoyable. And before we start, I think I have some borrows here. Cash. I'll just catch one. Oh. Anyone here? Okay. Last one. Want to try? Okay. Yay! We got a winner. Okay. Let's begin. My topic is accelerate your AI cloud infrastructure, but we don't do that we saw all these kind of AI cloud from the public cloud provider, but we use them, but you may don't know how it is really implemented from the low level. So there's a lot of different implementation based on different infrastructure. But here today we're looking on SUSE, Linux, and the KVM and QEMU. So let's begin. So first is a little bit introduction from myself. I'm working for the SUSE Labs. It's around 5 years now. And I'm mainly working on the I/O virtualization, which is the network before and the GPU today. And also working on the ARM64 virtualization. So my work is pretty close with all the vendors, like the NVIDIA, AMD, Intel, ARM, and customers sometimes for some solutions there. I'm personally also working on some AI, machine learning accelerator research there. So this is part of the research, today's topic. I think, that's me. And here's our... No, I wish. This is an astronaut from Mars, so we're kind of like him to do some exploration today. So today's agenda here, we'll have a quick brief on the AI cloud and hardware accelerator, have some basic idea. Then we'll take a look why we want to use NVIDIA GPU virtualization, and also we give you how we integrate partnership with NVIDIA, how to integrate GPU virtualization in our Linux. I also show you a demo after that, give you a basic idea how to really run a vGPU and in a VM and run some AI instance there. So last we'll just see the future, our future, vendors' future, and the community activity for the next move. So back to the AI topic again. So if you are a data scientist or you're working on some data research project, data development, you may be pretty familiar with this workflow here. So basically, we are going to face amount of data, do some training or do some mathematical algorithm, we call it, and then get a model out of it. This part, we call it training from the AI world. Once we got this model, this is not the purpose. We actually want to put it in use in a real product environment. And that's called another phase, the inference. And in that part, this model will make a decision for us. And that's what we call it machine learning. And that could do it all automatically. And if you work on that, if just yourself, you probably don't need any accelerator. But in reality is that you need to work on some quite big data there, like gigabyte or terabyte even. In that case, you really don't want to work it on CPU only. At that time, you may need some accelerator to do it. And these kind of three types in the current on the market. So the first is quite a mature product. We all know that. It's the GPU. Actually, we should call it the GPU, general purpose GPU. It's only for the computing. And we have this NVIDIA, AMD, and Intel. This is mainly used. Like I said, it could provide the OpenCL CUDA library. And if you are doing some training studies we just discussed earlier, you basically need the GPU there. But that's not the only option, like especially when speaking to the inference phase. There's other options, like the one, the FPGA here. It's actually already used by a lot of public cloud, like the Microsoft, the Azure cloud there. They're using FPGA. Not only for the AI workload, they even use that to accelerate their network. That's quite interesting. The other one is the most another popular one today, but it's not for training purpose or not on the server side, but it's more like in your mobile world, like the phone today. It also has AI chips there. That's actually the ASIC, and that could do some inference function there, and it like to process your image or some other purpose there. So anyway, we have this kind of a different accelerator. But back to the cloud, like the data center, we still need to focus on the GPU. Again, like if you're only working for yourself or you just do some scientific research, you probably don't need a cloud at all. But that's not the reality. In reality, actually AI workload is used like this way. So it's integrated with your the general cloud there inside your data center. It will manage all the physical resources and automatically. So in this case, when it comes to the accelerator, so there would be comes to the questions like in a general cloud there, we are running VM there. We know the benefit, like we can run multiple VMs in one physical VM. We can do a snapshot on it. We can do line migration, which is quite convenient for management. But can we do the same thing on the accelerator, especially the GPU? Earlier, the answer is no. It's difficult. Like at least from the hypervisor, from the virtualization stack, it doesn't support. This need the hardware has its own mechanism to do the management, like to snapshot its device state, and like we can restore a device state and then we resume it back, make it work. Based on that, we can do other cool stuff like migration and so on. So the real question is here, like how we fix these problems to fit a hardware accelerator to fit in a cloud. So now it comes to the GPU virtualization solution here. And so thinking about the three problems, we just discussed that, like can we run multiple devices on one real physical devices? That's actually a very cool function. Thinking about it today, you're buying a GPU, that would be $1,000. And especially if you are working for a team, there's 4 or 5 people there, you definitely don't want to buy each one for every people. So in this case, we really want to run multiple GPUs there, or we call vGPU, virtual GPUs there on one physical GPU. And then the second one, like, do we want to also do a snapshot for your device there? So like when we set up all the AI framework there, Like if you have done that, you probably remember. It's disaster. There are so many libraries, so many configurations. You really don't want to do every time you're working on a new project. So why don't we store a VM image there? So we finish the configuration, we save it. Next time, we just start a new copy of it. That won't be nice. And that needs the device to implement it. And that part comes to the vGPU manager here. It's kind of a module, kernel module, dedicated with the normal virtualization stack. It will operate on the GPU directly. It's kind of a alternative driver there, if we see that. So this vGPU manager could do a couple things. First, it's a scheduler there. It coordinates multiple vGPUs to share this GPU more efficient there. And it could also manage the device disk there. We can save it. We can do a snapshot there. We can restore it, resume it. And the other cool thing is we can also do monitoring. Like we want to check what kind of utility usage for the GPU today. What's the overload for this GPU? Like should we cool it down or should we fire it up? And that's another cool point. So that's a very good benefit to put GPU virtualization above the other hardware accelerator we saw there, like the FPGA and ASIC there. But only speaking of this part, NVIDIA is actually not better than Intel or AMD there. Because actually from the software perspective, Intel is earlier than AMD, than NVIDIA there. But as we all know, Intel doesn't have a dedicated GPU. It needs to use a system memory there. That limits its usage a lot. And AMD actually has a better hardware design. It uses a SRIOV mechanism there. So it actually implemented the resource splitting by the hardware. So that's more convenient. However, we still stick to the NVIDIA. And I think that's probably obvious today. Like if we check the software ecosystem today, it's basically dominated by the CUDA. And every data scientist couldn't bypass CUDA. Like even it could use OpenCL, but still most of the commercial product or stuff, they still rely on CUDA. The other side is NVIDIA, they evolves quite better. If you see the picture there, each generation, Pascal, Walter, and Ampere, they have significant performance improvement. That helps them to attract customers a lot. So anyway, we stick to this NVIDIA GPU Virtualization as the start point. So we partnership with them, we work close with their engineer, and we work on all the downstream implementation, and we provide a SUSE GPU virtualization solution from our side. So, like I said, so there's, because from the, we haven't talked a lot about the detail yet. If thinking a lot about the detail, so because the vGPU manager there, this is the kernel module, and it needs to communicate with other kernel modules and user-based libraries there, like the VFIO, MDEV, mediated device, and the QEMU, the VirtIO there. So it's a lot of work there. So it would be nice to provide it by a Linux distributor, and that's what we do. So we provide a reference platform for our customers there. And we start from the SUSE Enterprise, Linux Enterprise server there from the 15SP2, and the latest one is 15S3. We use it as the host. We deployed the kernel, the vGPU manager driver from NVIDIA, and we use our driver, we use our kernel, we use our QEMU there to make it work. For the guest VM side, we also tried a different couple choices there, mostly from SUSE Linux today, and also some Windows VM there. So, but mostly we focus on the functions there. Like we needed to make sure it works correctly. All the library, no library conflict, no kernel ABI conflict there. So we make sure their driver, the CUDA could run smoothly in a guest VM. And we also want this guest VM has the 3D graphic performance, even though like today is AI cloud, so 3D is totally a bonus plus bonus there. And also like the remote display, like the remote desk VDI, some stuff there. And we also tried the max vGPUs there, running multiple vGPUs, 4 vGPUs, even 16 vGPUs in one GPU there. And we made them work, but we also did a lot of performance optimization. We ran a lot of benchmark comparing it with the GPU pass-through there. GPU pass-through is more like to pass through one whole GPU into the guest VM. So it's exclusive, and it has the best performance for a VM scenario. The only bad part is it could only be used by one VM, and there's a lot of limitation on that. So we also tried the different vGPU types there, because that's the good part for the vGPU too. Like you have one vGPU, for example, you use the Volta or Ampere GPU there, but you can also run other vGPU types there based on it. And also there's a different profile for the vGPU. Like some GPU is for the application, some GPU is for a workstation, and some GPU is only for the computing purpose. We only support the workstation and computing there. So I'll give you more detail there. So this is some tests we get. So one interesting part is that when we're doing the graphic performance, and from the first line is the default, like we just enable it, we didn't do anything to change the configuration. And we noticed that if you see the Maya Medical SW, the performance is really bad. And we spent time there to figure out why it happens. And eventually we found that it's actually the FTL. Like if you play games, you're probably familiar with the frame time limiter. And it is enabled by default, but we disabled it manually. And we also did some other optimization, like to enable display from the QEMU level, and also like disable ECC for that. And then we got a much better performance. Like you see, from like 1/3 going to like 120% there. That's a huge improvement. And like I said, graphic, this is just the bonus performance. But the other one, the computer performance results, is actually quite stable. That surprised us. And it's quite similar. Like when we're using a vGPU, it's quite similar with the GPU pass-through case. And we think that maybe it's because the GPU, the data plane there is quite straightforward. It's not like the graphic. There's a lot of like it's going to the OpenGL, render, DRM, all the drivers there, the GM, and all the even the gas top that. That's so complicated the stack there. But for the computing side, it's just going to the CUDA or OpenCL and then going to the driver directly. Anyway, that gives us a very good GPU computer performance. That's also another insurance for us. So based on all the tests there, we found we managed to make our virtual GPU has the similar performance with the GPU pass-through. And we also found that no matter what kind of vGPU types you're doing that, like the workstation type or compute path, it has kind of a similar performance there. And we also saw that the performance is mainly decided by the hypervisor side. So no matter what kind of virtual VM there, like maybe we are using SUSE Linux or Red Hat or Ubuntu there, or even Windows there. It doesn't have too much difference. And we also running the multiple case. For example, we run 4 vGPUs there. So it's not quite good for like we run 4 GPUs at the same time, but it's still better than our expectation. Like we run 4 vGPUs at the same time. One GPU should be like at least 1/4 of the general performance. But our results show that it's much better than 1/4. It's going about 1/2 there. So that's an interesting fund there. So it at least gives us to know that if you run multiple vGPUs there, you should still have gains over it. And so we provide our solution, we make it a product, and we also implemented a lot of features there. Like you can run remote display, the VDI function, the graphic performance, we can support 3D, and the CUDA part, all kind of AI framework. This is done by another team, like AI and machine learning projects there, but it could all run where, or at least installment where inside a VM, guest VM there. And the computer performance, we also like the VM device snapshot there. We also provide line migration, but that's only technical preview, so we haven't really announced that. And the last part is the 800, the latest NVIDIA GPU architecture, Ampere architecture, Ampere 100. The biggest improvement that is 2 parts for this GPU. One is it also uses the same mechanism as AMD GPU we talked earlier. It uses a hardware mechanism called SRIOV. The other one is the MIG, the multiple instance. It's more like they put 7 GPUs in 1 GPU board there. So it actually has 7 GPU cores. You could use these cores to VM, or you can use it to container directly. That's yeah, I'll give a little bit for the future side. Like that's another focus. Like how do we provide device virtualization to container products there. So, and also we're also working on a security boot for vGPU. You see it's green, so we really haven't worked on that yet. So yeah, and I think from here you should know like how we really to put a hardware accelerator to make it work in an AI cloud. All the AI cloud we create an account there, we buy a instance there or drop plot there, and then we add a GPU there, And that's really how it's working, like one vGPU, actually just one piece of the full GPU. Here, I'll just show the demo. We can start from the beginning to have a more clear. So open source, sadly. And during the preparation, you need to go to the NVIDIA website. You need to register an account, get a license. You can get a 3-month trial license there. You need to download the vGPU manager from their side and install it in your host. You need also set up a license server. And so basically, you need to get a license from their side, generate a license bin file, and then you create a local license server. You create a license server in your local, and then you upload the bin file there, and then it makes it work. So it's not ideal, but I think it's still better than, how to say, like it's still better like it's by one GPU rather than by 5 GPU for your teams there. So I think that's probably still very popular there. A lot of, I think most of the Linux distro has this partnership with them, like Red Hat or Ubuntu. SUSE is also part of it. So here is actually I upload the license bin file to the local license server. So at the bottom is the document from SUSE. So you can get the full instruction there. And also I said this is already a product for us. If you run it, if you found any bugs, you can just create a bug from our Bugzilla. We are obligated to support it. Here is I'm already installed the vGPU manager there. Similar as the normal GPU driver, you can run the NVIDIA SMI to see it's there. And you can also see it actually uses the NVIDIA kernel module. It also uses the VFIO and MDV. That's we support there. So VFIO and MDV. And here is how I created a vGPU instance there. I'm actually using a UUID number there. You can see the 8400, that's the physical GPU. And I created this UUID, and I created, you can see there is a folder here. That's actually a vGPU. It has all the resources there for working. And here is we can remove it. Yeah, this you can check the detail. I'm actually created a V116C. Basically, it means this vGPU has 16 GB memory and for compute purpose. So I add it to a VM there. I already did. So this part is quite straightforward. You just add this command line there to pass through to the VM by the VFIO device platform. Now we do that. This is actually, you see a desktop based on a vGPU driver. I also did a little bit further, like to running a AI workload there. I'm not an expert on that side. I'm sure you could do better. Also, there's a lot of instruction. Instead, I choose to using NGC. You can call it the native GPU container or NVIDIA GPU container there. I just download it there and then run it inside the guest VM. So here is I'm doing This is actually, I'm already inside the guest VM. And we also run the NVIDIA SMI status check. It's all there. And I'm going to get this NGC container here. You also need to register a key there for security purpose. Yeah, that's kind of a downside to use NVIDIA product there. Luckily, it's only one-time step. Once you set it up, you don't need to do it again. This part is very similar with a Docker process there. You just find the image you want to use, and then you pull it from the remote registry. Here I'm trying to find a Tensor RT, the Tensor real time. Yeah, here I'm running the Docker to image. I already put it for time sieving. This is the one we're going to test. Now we just run the Docker commands there. Now we are getting into we already set up the GPU there. The GPUs we're using all. Now we're getting into the Docker environment. And I just run a Tensor RT engine there. Here I choose a enter 8 type. And this engine is kind of a model we already trained. So what I'm showing here is actually a inference status here. Voila, it's running here. And it shows successful. Mm-hmm. So by the time here, we actually set up a vGPU in your host side, in your host environment. Back to the AI cloud side, this would be like you don't know that this is all the detail. Like you run the VM, it's already set up there. You could just install the driver. They may already install the driver for you. You just check the NVIDIA-SMI to check the GPU status. And then you just pull the Docker image there and run the engine you want. What kind of image you want, engine you want to try? What kind of AI workload you want to test? Or you just want to start from the scratch to build it. But all this work we are running based on a GPU, a hardware accelerator, which would save a huge time there. And so that's basically the kind of the latest status for all these kind of virtual GPU. But let's take a little bit further to see how these kind of techniques going. What's the cutting edge part? So first is actually ARM side. I think ARM server is quite popular today. Everyone talking about, even NVIDIA, as we know, NVIDIA is trying to purchase ARM company there. And so we actually made it work on ARM server, but just the pass-through mode. We haven't done it with the vGPU manager side. But I have confidence that it will be soon. This would be driven by NVIDIA side, but that will be. The other side is the container side, the Kubernetes world. So like I said, vGPU could be working on our container directly, but before that, we can use the KubeVirt, a Kubernetes plugin to running virtual machine there. So we also confirmed that, we verified that we could make our vGPU working with the KubeVirt. So if you run your keyboard and start a VM there, and then you install the GPU, the hardware there, and you can just running all the container application directly. The other side is the Rust VMM world. So this is more like a light VM user scenario. Thinking about cutting edge, or not cutting edge, thinking about the edge computing, or we don't want a QEMU or other like heavy virtualization application there. So Amazon, they provide this called the Firecracker. And also the Rust VM side has this cloud hypervisor. And this is also a discussion there. For example, the Firecracker recently discussed about how to enable a PCI bus there, which could potentially support vGPU. So that's also expecting. From the other world, from the vendor world, as we know, the AI machine learning is so popular. Everyone wants to jump in to get a piece of it. So far, NVIDIA dominated it. And AMD is also quite positive. I think they already partnership with Microsoft Azure public cloud there. You could use a GPU instance on that platform. Intel is about to announce to release a dedicated GPU. So the rumor been there for years, but it's close and closer. Another benefit for Intel is that they have a very good FPGA products there. So somehow you could still use their FPGA to do some inference acceleration there. And ARM side is also ambitious. So they have Samsung actually working on a similar mechanism there as the NVIDIA Ampere, the MIG, like to put multiple GPU cores in one board. So basically you have multiple GPUs. It's not a vGPU, it's more like multiple GPU cores, GPUs their arbiter, and to do all the coordination and run it in one SoC. The other one is from the other solution, the ARM, the Mali GPU. They also has a similar mechanism as the Intel there to do the software implementation. And it's also ongoing. And for the last part is how to use device virtualization in a containerization environment. And that's quite new. NVIDIA has their GPU operator. You could use that for Kubernetes directly. It could be used as the plugin there. And the MIG, we just discussed that. It could be used by, like, run the Docker there. When we set up the commands there, we can just give one piece of the MIG there. So that, and from the community side, and we have this scalable I/O mode there. So that's basically that's a huge improvement, a huge feature there. So it could make the vGPU or virtual device there could be used by container directly. So I would say this is a quite interesting, quite excited. There's a quite exciting party outside. So looking forward what will come next. I think that's all for my today, and I hope you find something useful from side. So thank you again for your time. And if you have any questions, feel free to ask. I would be more than happy to answer. Thank you. Any question? Okay. Yeah, if you're interested with this slides, you can get, I think I sent it to the organizer here, or you can reach me. I will be pleased to send you. Also, like if you want to discuss further on all this stuff, I'm happy to be talked to it. Okay, thank you. Thanks.